Hello everyone, my name is Sebastian Gabriel, and today I will present to you a topic with quite a long title, Automatic Code Generation for Malware Detection based on MITRE ATT&CK. In this presentation, I will describe to you the task at hand. We will see an overview about how translators work, banal implementation of code generation, how we can actually improve it, and after that, we'll move on to our problem specifically. We will discuss about MITRE ATT&CK database, how we approached our problem, what's our contribution, and some of the challenges, ending with a conclusion and some future work. First of all, let's describe our problem. Code generation from natural language represents the process of creating source code from natural language text. In the literature, this problem has been approached from multiple points of view, depending on its input and output. As an input, we can either have a code description or a code description alongside the test case for the desired portion of code. We have to look at that code description as a abstractization or a summary of that output program. And the more information we give, the better the model will behave. As an output, things are kind of straightforward. It can be for the program's code, which should be technically be compilable or runnable, or a code snippet, which is just a small part of the whole program that just handles the logic that the user needs. This problem was first viewed as a simple translation problem because we actually want to translate natural language to machine language. Okay, so let's build on that and try to understand this task better. We will have a small technical overview about how this task is actually solved, so bear with me. And then we will talk about some of the actual problems. The general architecture is called encoder-decoder, with the intuition being that we have to transform the source language into an understanding of that sentence for the model. And then that understanding needs to be converted into the target language. On the top right of the screen, you can actually see this architecture, which has the input x0 to x2, which is encoded in this network, after which the model does some computation inside this hidden state, after which the result is decoded, and we can see it as an output y0 to y3. As compared to other machine learning models, both the input and the output are of variable length because, well, both the input sentence and the output sentence may have any length possible. The variable input length is usually solved by padding. Just add some data without any meaning to the end of our sentences in order to have them in the end of the same length. For the output, a recurrent neural network is used. Basically, we just pass some state and generate the output sentence word by word, updating that state at each iteration. This recurrent neural network can be seen on the bottom right of the screen, where we basically output the state, which is V, and the token L, which represents our current token. That state we just outputted is enters again in our model to output the next token, and so on. The general architecture looks like this. Here's the encoder, and this layer just converts the our description words to numbers because we have to work with numbers inside our models. Then those are inputted into a bidirectional LSTM. We can expect that if we actually input a sentence of a longer length with more details about what we want our program to do, we will get a more accurate code than that of a shorter sentence with less details. That's what this layer does. It actually predicts what the meaning is based on some future information so that their final outputs are similar. The attention network assigns each word a score based on its importance. If a word is more important, then it has a higher score. If it's less important, it has a lower score. As for the decoder, the LSTM does the meaning prediction based on the current context, and the linear layer combines everything together while the softmax picks the next best word. When we actually want to evaluate this model, we have the standard accuracy, but when translating, we might have two possible valid translations for the same input sentence. This is why the below metric was introduced, because it computes how much of the given words occur in a similar context in our database. Here we can actually see an example. For example, we generated the sentence "the cat is on the map," and we have to compare it to the data set entry "there is a cat on the map." What we do is we compute groups of two consecutive words, which can be seen right here, and we see how many of these groups in our first sentence match with the database. Highlighted at the matching words, and you can see that there are 2 out of 5 groups in our first sentence. So score is 2 out of 5. So up until now, we can basically generate code from natural language token by token. Well, when thinking about code, its syntax is way more strict than that of a regular language. And when this syntax is violated, the code is not even working. So it will require lots of manual work in order to run. So when taking this into consideration, we have to actually generate a structured sequence of tokens instead just of a simple sentence. And thus, we have to generate something called abstract syntax tree, which is something like a tree-like representation of the code. Instead of text, it's a hierarchical structure. And it represents the relationships in the code, and it can be converted into code easily, and vice versa also. While also maintaining the code error tree, syntax error tree. On the left side of the screen, you can see a section of code, while on the right side, you can see its corresponding abstract syntax tree. This tree contains information about its syntax. For example, if we look at this while node, we can see that in the condition, we compare our variable b with a constant 0. And this is what the first line of code does. It compares b to 0. All right. And for generating abstract syntax trees, we require kind of lots more information about our data besides the input text and the state that dictates the next node that has to be generated. We will have to predict nodes instead of words for this tree. So we require some more context, such as the parent node, because two nodes might differ to this parent, or one of his siblings. With the intuition being that since multiple nodes might have the same parent, they might differ to this sibling. Here we can actually see how the generation takes place. As an input, we have to sort a list in descending order. And the output can be seen right here on the bottom right side of the screen. How this works is that we know that our code starts with root. And so we input this root and our description to our model. And our model should give us this EXPR. Then we have the EXPR and our input, and we input it forward to our model in order to get this expression out of value. Things are quite similar until we generate this first branch, after which, if we look at these two nodes, they have the same parent, which is call, and the same input. So we have to make a distinction between these two. What we do is pass this last token generated to the next child of call, so that they will have the model will have a chance to generate something else besides this expression of the function. Right. This diagram is our parent model architecture. Don't imagine that we did anything complicated here. We just appended the parent state and the sibling to our initial architecture, which have to be concatenated to our description after we compute each word's importance. All right, now we have everything that we need to actually generate code for some task. So let's dive into our specific problem. At this point, I believe that many of you wonder what that MITRE ATT&CK was. Well, it's basically an open source database accessible from anywhere, which contains lots of information about attack vectors, and most importantly, tactics which are used by attackers during a cyber attack. These tactics are our main star in this problem. They are the descriptions inputted into our model, since they describe methods and procedures used by attackers in the cyber attack. In general, these tactics are used by cybersecurity professionals in order to enhance the system security, but also MITRE tactics are recognized globally, which led to the development of antivirus tests, which an antivirus has to detect which tactic specifically has been used during an attack. Here we can actually see how an anti-now database looks like. On the left side, we have the entity description, which reads that attackers may create a new process with an existing token to escalate some privileges. On the right side, we have the corresponding code in which we iterate to each process, check if that process is a valid one, check if the path is the same as the program recommended in the description, and then we check if it was learned by the user. All right, here are some statistics about our dataset. In total, there are 411 MITRE techniques, out of which only 102 have implementation. So there is a clear need for some helpful programmers. The sentences are a bit lengthy at about 62.1 words per description. When looking at the nodes in our trees, we have 462 nodes per code. So we can actually conclude that this is quite a difficult data to generate code from, because we have little information to learn from and a lot of information that has to be generated. As for the steps taken to create this model, we have to collect all the necessary data for it, and thus we scrape the MITRE website and Bitbuckets to get the tactics and their implementation respectively. After we pair them, we have to preprocess our data set. First, since we want to generate abstract syntax trees, we have to convert our plain text code into a tree, followed by linearizing the tree to a list using depth first search in order to give our model a list to learn from it. The reprocessing for text is minimum station task. We just lowercase the text, tokenize it, and prefix it with a start token and suffix it with an end token. As for contributions, there are quite a lot of things that have to be noted. First, in the literature, abstract syntax trees were generated with the help of grammar rules, which are basically just some kind of wrappers for our nodes. In our case, we generate the abstract syntax trees directly, which lowers the number of generated nodes, and thus our model is much more accurate. Moreover, we generate code for an internal language whose implementation requires a lot more general approach, since there isn't that much data available for it. So it has even more potential for languages with resources. Also, our model would have a quite technical usage compared to others. So dataset, usually in technical cases, a dataset has much more noise and it's harder to learn from. Since we're learning on a small dataset, the encoding layer might struggle a bit to extract knowledge from the description. This is why we'll replace it with Roberta, which is a print-trained model, in order to increase our model's performance. Another contribution is the fact that we're going to generate the structure of the code, because it seems that the generation of other dynamic data in the code, such as variable names or strings, is another problem altogether, and it should be treated as such. But it would be brave to assume that everything was presented as at first. We encountered some issues regarding our generative model. As I have previously said, we input to our model the description, the parent, and the last node on the previous branch. But what if two consecutive branches are exactly the same? Well, our model might get stuck in an infinite loop. In the literature, this was solved by limiting the number of branches that can be generated. What we did is that we only generate a new branch on request, and the user can actually pick from multiple possibilities which one he prefers. This was the perfect way to strike a balance between the user implication in the coding process and the assistance of our model. Moreover, the evaluation metric might be one of the sources of error in this translation task. It actually evaluates only the syntax without taking into consideration the meaning of the generated sequence. The downside is that we actually have no alternative for this metric at this moment. The results are kind of interesting, considering that we only have about 100 samples. We obtain higher results than the state of the art on the Hudson dataset, which is actually the standard dataset in our domain. And when compared to the Django dataset, we obtain a lower result, but that is mostly because in its descriptions, the Django dataset kind of duplicates the code. For example, there are a few lines that says import this library, and in description, this reads that this line imports this library. So although our dataset is harder to generate code from, and although we have more descriptions, the model has some impressive results, not to mention that there is a clear improvement on the beta model compared to the base model. In conclusion, I would like to point out that this whole process of using automated code still requires human intervention, and it must be used in conjunction with good programming practices such as code reviews. And in the end, it's still a machine learning algorithm, so it would be best for generative repetitive code, while it might struggle to generate unseen stuff, which would be the case for new attack vectors. As for the future work, we want to build the second component of this model, which would solve the problem of generating dynamic data such as variable names. And thus, we would have a fully runnable code when we will be implementing these two components together. And as a bonus, I also have a demo for you. All right, we actually were able to implement our model inside an extension of VS Code, which is just a programming environment. To activate our extension, we have to manually activate it from here, and then we are able to type code automatically by a keyword combination. For example, when I press Control space, I can actually select from here or, and then inside it we can iterate to something. As I previously mentioned, our model generates only the structure of the code and not variable data, such as variable names. So when we try to generate something from this, it will point out an error as a code because we have these missing statements that have to be completed. So I'll type just something completely random here, and we're able to generate stuff continuously now. So this was it from our presentation. Thank you for your attention. Do you have any questions?